Welcome. The integrated rate law from the table. Believe me when I tell you this, if you master this table, it's over. Now, remember this is zero order, this is first order, this is second order. Now, in this rate law, this table that is on the board is extremely powerful. I summarize everything you need to know here. Let's go. The rate law in zero order is equal to K. Because why is it equal to K? If I put the initial concentration here to be 0, if my initial concentration is 0, anything raised to the power of 0 is 1. Let me just leave it like this for clarification's sake. But the rate is equal to rate constant in zero order. Now, look at what is happening here. If I increase the concentration of A, let me say by 2, what will happen to the rate? The rate would increase. Look at it. 2 raised to the power of 0 is 1. So the rate will remain the same in zero order. Examination question. If in zero order I increase the rate by 3 raised to the power of 0, what will happen to the rate? If I increase the initial concentration by 3, what will happen to the rate? The rate will remain the same. And that is why we just said that R is equal to K. Come to the first order. If I increase the rate by a factor of 2, if I increase the concentration by a factor of 2 raised to the power of 1, what will happen to the rate? The rate will also be increased by a factor of 2. It will double. If I triple the initial concentration, the concentration of the first order by 3, the rate will also increase by 3. If I increase it by 4 raised to the power of 1, the rate will also increase by 4. Examination question. What will happen in second order? If I increase the concentration of second order by 2, what will happen to the rate? The rate, 2 raised to the power of 2 will give you 4. The rate will increase by a factor of 4. If I increase the concentration to be 3 raised to the power of 2 will give you 9. The rate will increase to what? 9. If I give you 6, I increase the concentration of second order by 2 raised to the power of this will give you 36. That is what is going to happen to the rate. During the beginning of this video, we talked about the unit of the rate constant K. It's on my play channel. Some people have issue with locating my play channel. All you need to do is tap on my name, that profile picture on my name, tap it and it will take you to my playlist immediately. Now, if you go to my playlist, you will know that I did a video on the unit of the rate constant K, where I told you that the unit K, there is a formula to calculate it, and the formula is for K is M 1 minus M T minus 1. I said it. It's on my channel. Check it out. Now, if you want to know the unit of the zero order, it means that N here, that N is equal to 0. Right? Let me write it here. K is equal to M 1 minus M T minus 1. So for zero order, it means that N is equal to 0. So if you substitute it here, you will get this answer. For first order, n is equal to 2. If you put it here, 1 minus 1 will give you m0 t minus 1, which is the same thing as or t raised to the power of minus 1. That is the unit for first order. The same thing is happening for second order. If you put 2 here, 1 minus 2 will give you minus 1. And that's why I get m minus 1 t minus 1. That is it for the unit. Let's go. The half-life under zero order, you have to cram it. You have to know the formula. Because during the course of this video, I will give you a question and I ask you to calculate the half-life for the zero order. If you do not know the formula to use, you cannot be able to calculate it. I can come and tell you to calculate the half-life for first order, for second order. If you do not know the formula, you can never solve it. I can come and ask you to calculate. I can give you the initial concentration, give you the final concentration, give you the rate constant K, and ask you to calculate the time. If you do not know the formula for zero, second, or third order, you can't be able to solve it. And that's why I just took my time to write it on the board like this. And I'm explaining it one after the other. Now, the half-life for zero order is this. The initial concentration of A all over 2K. This is length 2 all over K. Why this is 1 all over K and initial concentration of A. Now let's do it. An examination question can come out from here. Now you can see from here that there is no let me start from first order here. Look at it, you can see that the half-life is independent of the initial concentration. Why the half-life for zero order and they are all dependent on the initial concentration? Because you can see that the initial concentration are all here. That is an examination question. Now we are into the integrated rate law. When I start solving calculation on this stuff, you understand why I'm taking my time to explain this formula. Now, when we talk about the first order, this is the formula for zero order. This is the formula for first order integrated rate law. This is the formula for the third order, the second order. Now, listen. We want to talk about the slope. There is a formula in mathematics. This formula, y is equal to mx plus b. The name of this formula is slope-intercept formula. Slope-intercept formula. Now, it means that from here, if you want to plot this now, it means that y is AF. And from here, that your m is minus k. And your intercept is initial concentration of k. So from here, the slope of zero order is minus k. That's a negative value. The same thing is here. If you apply y is equal to mx plus b, you will see that the slope here, that m is minus k. Now, if you plot this same thing here, y is equal to mx plus b here, you will now see that this is not minus. That the slope for second order is plus k. That is an examination question. Now, how do the graph of zero order, first order, and third order looks like? The graph of first order, second order, and third order. You can see when I plot a graph of the concentration of A versus time, you can see that, look at it, that you can see clearly at the bottom. Look at the one of zero order, you will see that it has a down slope. Why? Because from here, we already calculate that the slope is negative, so it goes like this. And look at it, I'm plotting a graph of A versus T. Look at for zero order, because when you use mx plus b, of course your y-intercept is link A. Look at it, not A. Here, if you plot y is equal to mx plus b, so I want to plot y against x. So my y is A, the concentration of A here. Can you see it? But here my y is the link of the concentration of A. That's why I'm putting link A for first order. But then my x is t, and that's why here I have t and t. So I'm plotting y against x, but it should be link A versus t. Now let's continue. When you come here, the slope is positive. So it's a positive slope, and that's why it's like this. But you can see that it's not from the origin. Look at it very well. And if you compare it with y is equal to mx plus b, you know that here that your y as this is 1 over concentration of A versus t. So this is how the graph looks like. Now this is the possible examination question they can ask you from this graph. You have to know how it looks like. You have to know how the formula works. Now, in order to make sense of this all long talk, let's go to example proper. You have to understand the unit too. Please, as you are watching this video, always like the video and drop a comment. Thank you very much. The first example, an initial concentration of a reactant in a zero order. Can you see it in a zero order? Is, so that means that your A0 is 0.75 molarity. The rate constant K, so your K is 0.015 mole per minute. what will be the concentration of the reactant after 15 minutes? So your time is 15 minutes. So he wants you, what will be the final concentration is what you want. Now, that is the reason why I wasted my time explaining that table for you. Now you can see that from this question, all you need to do, you know the reaction is in zero order. Now for you to proceed, another thing you should do is change the unit of the time and that of the rate constant K. Remember, in one of my videos, another unit of rate constant, we said that K is M1 minus N 2 minus 1. And I told you that C can be in minutes, seconds, hour, time, day, years. So now, what I'm telling you to look at, so why I'm saying this thing is that so that you should know if you are going to convert or will leave it like that. So since the rate constant K is a minute and the time is a minute, so no need for conversion. Now all you need to do right now is for you to write the formula for the zero order, and then your answer will flow naturally. That's what I was telling you. The integrated rate law for zero order, you just write it. Now from earlier we said that the concentration final is minus KT plus the initial concentration. That's all. Now they want us to find the final, so all you need to do is just infuse this into it. So this will give you equals to minus 0.015, right? Molarity all over minute times your time is in 15 minutes. So this minute will cancel this minute. Plus your initial concentration is 0.75 molarity. Okay. So if you times and plug this thing together, punch it in your calculator straight, you get 0.520 molarity. So your initial concentration is this. Now, can you see how easy it is? But if you don't know the formula, the one on that table, you cannot answer this question. Let's go to the next example, please. Now, the B part is how long will it take the concentration to be reduced? So now they want us to know the time. They want us to know the time. Now remember, the final concentration has been given now. It has been reduced to 0.06 molarity. Now they want you to calculate the time now. But then the initial concentration has always been given from the question. So from here, the initial concentration is 0.5, don't forget. 0.75. Now remember that AF is minus KT plus A0. Now they want us to calculate the time. So from here, we just impute our values. Now, what is it that we don't have here again? From here, if you want, we have our K, it's already been given. Our K is what from the equation? 0.05 molarity per minute, right? Now we just insert it here. So we have 0.06 is equal to minus 0.015 T plus 0.75. So I will collect lifetimes here. This is 0.06 minus 0.75 is equal to minus 0.15 T. Now 0.06 minus this should give you minus 0.69, which is equal to minus 0.015 T. Now T is minus 0.69 divided by minus 0.015, and that should give you an answer of 46. Of course, it has to be in minutes because your K, you use your K to be in minutes. Please always pay attention to this. Now that is all for that question. Let's go to example number 2. The more I solve it, the more you realize that this is so very easy. Check out this example. Calculate the initial concentration of a reactant that took 4.7 minutes for it to reach a final concentration of 0.15 molarity. The rate constant is given. This question is tricky. They do not specify if it is zero order, first order, or second order. They just gave you this question. How can you know? You can only know by looking at the unit of the rate constant. Look at this unit. We have m minus 1 s minus 1, which using this our formula, that this is m. Which what will you put here to give you this? The only thing you can put here is when n is equals to 2. That's the only thing, because when n is equals to 2, this will give you minus 1 minus s. So sometimes when they do not signify the order, you have to use this formula to know which order you are solving. So this is second order, and the integrated rate law formula for second order is 1 all over f final is equals to kt plus 1 all over f initial. Now they want you to calculate the initial concentration, having given you the whole stuff you need. So from here it's easy. So this is will give you 1 all over 0.15 to be equal to your k is 2.5 times 10 raised to the power of minus 3. Your t time is in minutes. Now you cannot use this time. Why? The concentration of k is in seconds. Look at it very well. So we have to convert. We have to convert this time to seconds. So what we will do now is 4.7 times 60. That should give you 282 seconds, right? So what we use is 282 seconds. Now, plus 1 all over, this is the initial concentration we were asked to find. So if you calculate this very well, if you punch it in your calculator very well, this should give you 6.667, which is equal to 0.705. You times this to this, then plus 1 all over A, concentration of A initial. So collecting lighter, this will come here, and what you get is 5.029 is equal to 1 all over A0. Now, what we want to calculate is A0. So from here, if I want to calculate the initial concentration of A, the answer is 1 all over, because this is 1 all over. So if I invert it, this will give me 1 all over this 0.2. If you put it in your calculator, what you should get is 0.1677 molarity. Why did I use molarity? The concentration is always in molarity. The concentration of either A final or A0 will always be in molarity. Always. Using what I just did right now, what is the half-life for a reaction with the rate constant of this? It's only in seconds. So we have m1 minus m t minus 1. What is going to make this thing to be in seconds is when n is equals to 1, because if you put 1 here, this will give you m raised to the power of 0 t minus 1. So this is first order, right? Good. Because this one will give you t minus 1. And I told you that the time can be in seconds, in minutes, in hours, in days, in years. And the half-life for a zero order is just ln 2 all over k from the table. And ln 2 is 0.693147 all over your k, which is 0.0045. You punch it in your calculator, this should give you 154 seconds. And that's the answer. So in a situation where they do not give you the rate constant, the order of the reaction, you have to use the unit of the rate constant K to determine the unit of the reaction. The example number 4, you have a data that shows the reactant with respect to zero order. They give you the concentration and the time. What is the value of the rate constant K? Now, if you look at this, we have the initial concentration, we have the time, and you have the table. Remember, for a zero order reaction, that K is equal to minus slope. Because when you have a question like this, all you have to get is the slope first. But remember, for a zero order, the slope is minus K. For a first order, the slope is minus K. For a second order, the slope is plus K. Now, if this is equal to minus K, and the formula for calculating slope is equal to change in y all over change in x. which will give you y2 minus y1 all over x2 minus x1. Now, we are dealing with concentration all over time. So that means that this will give me changing the concentration all over changing time, right? So in this question right now, it has to be the final concentration all over the initial concentration, meaning this minus this all over the time here minus the initial time. So this will give you 0.160 minus 0.800. All over, what is your time difference? 40 minus 0. Now, if you punch it, what you will get here, if you divide it, you should get 0.016 minus 0.016. And remember, this from here, it is molarity. This is the SI unit here is molarity, here is second. So the SI unit here is molarity per second. But you are not done. You only got the slope. And we're going to go to the minus. Remember, the K from first order is equal to minus slope. Now, there is minus here, and your slope contains minus. So here is minus from the formula, right here, minus 0.016. And this time, this will give you plus 0.016 molarity per second. Please note this, the rate constant K can never be negative. It is always a positive number. That is an examination question. If they give you something and you solve and your rate constant is positive, you already failed. It's always going to be a positive number. That should be all for this video. Please give me a thumbs up, comment on this video, and subscribe to my channel to enable me to be motivated to do more. Thank you very much.